So, all right, WebSockets. Actually, let me zoom out to the course website for 1 second. And close this. So we are starting homework 3. So homework 3 is released. Homework 3 content, I like releasing the homeworks the Monday of the new module, which means I stayed up really late last night after the Bills game, refining this homework for this semester. So homework 3, WebSockets and databases. I could add and APIs. There's kind of 3 separate topics here. Am I logged in? Sure, we'll change the title. So this is the new homework. It's what it says here, WebSockets. This week, we're going to spend 3 lectures talking about WebSockets. Today, we're going to cover the entirety of Objective 1. You'll be able to do Objective 1 after today's lecture. Objective 2 after Wednesday's lecture. Then we're going to move into databases. We're going to build a simple chat app using WebSockets. Like the other homeworks, you're free to modify what is actually being done with the WebSockets. If you just want to stick with the chat app, use my sample code. You might have to expand on it a little bit, but not too much to get it working. It's client side, and then server side, obviously, you implement the whole thing. But if you want to do something other than chat, I have chat with username and chat message. As long as you have 2 pieces of data, at least, you can change that into whatever you want. If you want to build a game for your server, that might be a little ambitious. I don't recommend that unless you have a firm grasp on all the content. But you're free to change that. Objective 1 and 2 is getting the chat working with live updates using WebSockets. So we saw with polling and long polling especially, we could get live updates from a server. So a user can input a message into the chat. It goes to the server and immediately goes to all other users. We're going to get that same functionality with WebSockets. And after Objectives 1 and 2, you'll have that functionality. Objective 3, we're going to add a database and Docker Compose to your app. So we're no longer going to be using Docker. We'll be using Docker Compose instead. Docker Compose is a way to have multiple containers running and able to communicate with each other. So we'll use Docker Compose to spin up 1 container for your database, 1 container for your server. Which a container for your server is the same thing you've been doing all along. We're going to add a database and then have the server able to communicate with the database to, of course, store data and do all our database stuff. So add that database to the chat. So when a new user comes into the chat, they can get all of the chat history and have that persist through a server restart. So we should be able to restart Docker, restart your containers, and be able, is this me in a different, yeah, it's me in a different tab. You should be able to restart your containers, and that data should persist. The database, the whole idea of a database is if your app does restart, the data is on disk, not in RAM. So after a restart, when RAM is flushed, RAM is all freed up, you still have your data after that. So that's the goal that we want for Objective 3. Add a database to your chat. And then the next 2 objectives, 4 and 5, it's really 1 big objective, but it was enough work that it should be split into 2. I want you to get credit for 2 objectives for doing this, is APIs. We're going to build a RESTful API that's going to create user accounts. And we're going to use a CRUD model. This will be the 3rd week of this objective. It basically goes in weeks. This week, WebSockets. Next week, databases. Week 3, RESTful APIs and CRUD. So this is a way to be able to create, retrieve, update, and delete data in a fairly standard way. So we're going to create paths to be able to create a user account. A user is going to have email and username. Retrieve all user accounts. Retrieve a specific user by ID. Update a specific user by ID. And we're going to use the put request type for this to update the username and or email address of a user, and delete a user using the delete request type. So that's what we're headed for the next 3 weeks. Any quick questions about this before we dive into WebSockets? And again, a reminder, I don't know if I have to keep reminding this, but I have the Discord lecture channel open. If you have questions, put them in there, or old-fashioned, raise your hand. All right, let's do this. WebSockets from scratch. This is good stuff. Okay, so we saw Ajax, polling, long polling, we saw these things fairly briefly on Friday, to be honest. I go through that pretty quick because it's not something I'm asking you to do, but it is stuff that you should be aware of. If you're going into the world of web development, you don't know what polling, long polling, well, Ajax requests you will end up using. But if you don't know what polling and long polling are, it's just a bad look. So I want to make sure you're familiar with them. Polling, so Ajax is when we're sending a request after the page loads. We're writing some JavaScript code to be able to send a request to the server, get the response, and process the response all in JavaScript without a page reload. So far, before Ajax, the only way we know how to get more information from the server is to send it a request, get a response. That response would be HTML, and we'd render the HTML to the page using the browser. And that would, of course, trigger a page reload. So with Ajax, we can get specific information. We can get raw data, is typically why we use Ajax requests. We can get raw data from the server after the page loads. So when you go to pretty much any modern website these days, the page loads, you get the HTML and the CSS right away. Then you get the JavaScript runs, fires off a whole bunch of Ajax requests, and then as the Ajax requests respond, that's when the actual data populates on the page. And you can go to the network tab of a modern site, which is pretty much any site out there these days, and watch all the requests come in. Like after the page loads, you'll see something with the first few requests, and then you'll see a whole bunch more requests come in as all the data populates. Polling is a way of continuously asking the server, hey, do you have new information for me? Do you have new information for you? Do you have more information for me? Polling is sending a specific Ajax request. So like if we want our chat app or any interactive app with our users where the data is constantly updating, usually updated by other users. That's where web apps really get interesting, is when users can interact with each other. Without users interacting with each other, I mean, there's a lot of great stuff, blogs, I guess, news articles and stuff. But it's really when users interact with each other where the internet becomes what it is today. It wouldn't be what it is today, in my opinion at least, if it was just users not interacting with each other. It'd basically be like electronic newspapers. That's an oversimplification. The internet'd still be cool. But anyway, users interacting with each other, in my opinion, is what makes the internet cool. I don't know. It's what makes it interesting. So information is constantly being updated. Users are sending more information to the server. Polling is a way of sending these Ajax requests. Give me the new data at regular intervals. So polling is saying, okay, every 1 second, I'm going to send a GET request for the new information, receive that information, and then render it on the page. The downside to this is you have to wait at most, whatever your polling interval is. If it's 1 second, you have to wait at most 1 second for that response. So there's delays, things are a little laggy, and there's a lot of network traffic. Even if nothing's updating, you're sending a request per second per user, which is a ridiculous amount of requests to handle. So long polling comes in to fix those downsides. Long polling is where a client will send a long poll request, and then if the server has information to send, it responds with that information. If not, the server just hangs and waits for there to be information available, and then responds to the long polling request, or times out after 10, 20 seconds. It'll respond. And you can see in the network tab, if an app is using long polling, you'll see all these requests that take 15, especially if nothing's happening. 15 seconds, and then a brand new one for 15 seconds, brand new one for 15 seconds. And whenever the server responds to the long poll request, the client immediately sends another long poll request. So the effect is we always have a long poll request open and hanging for every user. And whenever information updates, we respond to all of the long poll requests. Okay. So long polling isn't a bad solution. It's fairly effective. It's fairly efficient, but it can be a pain to implement. If I asked you to implement long polling on a server, you'd be able to do it, but it'd be, in my opinion, a lot of pain for what it's worth. I think you'd go through a lot of pain without learning too much new cool stuff about the web. So we're going to do WebSockets. This is going to create a two-way communication between client and server. So the client, we already have a way for the client to send messages to the server in HTTP requests. That's the standard way that we do things. That's how we do business on the web. That's how at least we start our business on the web. And the user can send Ajax requests to send HTTP requests at any time after the page loads. Cool. What happens when the server wants to communicate to the users? What happens when we get new information, we want to send it? Okay, we can do long polling, we can set all that up. WebSocket says, let's simplify that a little bit and get rid of all of the overhead and all the complexity of long polling and just keep the TCP socket open and use that TCP socket for two-way communication. TCP sockets are made for two-way communication, for an open connection, and for streaming data back and forth over the internet. That's what TCP is made for. With HTTP, we have HTTP as a request response protocol. So we open up a TCP connection, get a request, respond with the response, and then after that, we can close down the connection. For our purposes in this class, we usually close down the connection. Modern browsers and servers, they'll keep the connection open to reduce a little bit of a minor amount of overhead. That adds up, of course. Leave that TCP connection open for like the HTML, CSS, and JavaScript, and images, static files. They'll use that one TCP connection. But the connection can end after each request. So we're really wasting that TCP connection. Even if we do keep it open for multiple requests, we're not allowing the server to send anything to the user without there being a request. So we're wasting a lot of the potential of TCP by closing that connection potentially, or at the very least leaving the connection open, but waiting for a client action to respond to, a client request to respond to. It's kind of, I don't know, kind of silly. WebSockets, with WebSockets we say, just keep that TCP connection open, man. Why don't we just leave that open? That's what WebSockets are. So with WebSockets, we're going to get an HTTP request over that TCP socket. That request is going to be a request for a TCP, for a WebSocket connection. The request is going to say, I would like to use this TCP connection that we've already established for me to send this HTTP request to you. I would like to continue to use this TCP connection as a WebSocket connection. The server is going to respond by saying, yeah, that sounds good. Let's upgrade this TCP connection from HTTP. We're no longer going to use the HTTP protocol, but let's use the WebSocket protocol for this TCP connection. We keep the connection alive, and then we communicate using WebSocket Frames over that connection. Frames we're going to talk about on Wednesday. I'll introduce them briefly today, but we're going to talk about establishing that connection, how exactly that connection is established today. Yes?
Since it's a TCP socket that stays open, is there like a certain limit to how many WebSockets can really be in use concurrently on a server, or like depending on the server?
Yes. So the question, is there a limit to the number of TCP connections that can remain open using WebSockets? Yes, it's going to depend on implementation and hardware. There's always going to be some hardware limitations. I don't know how much I want to go down this question. It is a juicy question, though. So for example, if each WebSocket connection is each TCP connection has its own thread, for example. Threads are pretty heavyweight. So once you start having thousands of concurrent users, and each user has its own thread for the TCP connection, for the WebSocket connection, that's going to be limiting really fast. But if we have something, some form of lightweight threads, where we're not actually creating a new literal thread on the processor for each connection, then we can have tons more connections and a lot better concurrency. Like in 1.16 when we use actors, those are lightweight threads. We can have lightweight concurrency, I should say, where there's a lot of thread sharing between each concurrent piece of code that's running. So if we set it up like that, then we can have far, far more connections, as long as we're not being wasteful with our CPU resources, with our processor resources. And if you're interested in that more, it's called the 10KC, I forget what the acronym is, but 10,000 concurrent users problem. That's kind of a ceiling for threaded apps. No matter what you do, you're not really getting past that 10,000 concurrent users. You're not really getting up to that. So lightweight concurrency kind of comes in to address that problem and have 10,000 concurrent users, which would mean 10,000 concurrent WebSocket connections simultaneously without breaking a sweat. Then we can go up to like hundreds of thousands and millions. Once we get up to those numbers, we need some distributed architectures, though.
Just a quick follow-up on that. As far as like the lightweight threading versus like if the WebSocket was on its own thread, is there like from the user's point of view a big performance difference or not really?
From the user, no. Unless the server is actually bogged down and lagging, the user won't know or care. As long as the server can keep up. All right, so to establish this connection, we're going to initiate what's called, we're going to go through the WebSocket Handshake. So similar to like TCP, to establish a TCP connection, we have a handshake to make sure that both ends of the connection speak the right protocol. We have that three-way TCP handshake where we send the sync and ACK packages back and forth. We add one and do just a little bit of processing to make sure that we're both on the same page, client and server. If we are both on the same page and we both verify that the other side speaks the protocol, we have that TCP connection and we start sending information back and forth. We want to do the same thing with WebSockets. When we get that upgrade request, there's a very, very specific handshake that has to occur. And if anything goes wrong with this handshake, the connection is not upgraded to a WebSocket connection. So let's go through this handshake and go through each of the steps. So the WebSocket handshake, we're going to get a GET request for whatever path we're listening for WebSocket connections on. So this is going to be a GET request for a specific path. I think for the homework I kept it as /socket, I believe. So you'll have some specific path where you're listening for WebSocket connections. And then in your JavaScript on the browser side, on the client side, you'll have code to send a WebSocket request to that path. That request has to have these headers. And on the client side, by the way, the browser takes care of pretty much everything for us. We don't have to think too much about the browser side. It's the client side, or the server side that we have to do a lot of work with. But the browser is going to set these three headers: connection, upgrade, upgrade WebSocket. So this is saying, I want to upgrade this connection. I want to upgrade that connection to WebSockets. And here's my WebSocket key. It'll be a header exactly named this, sec WebSocket key. It's going to have some random value. Every single time any browser creates a WebSocket connection, even if it's the same exact browser and somebody just hit refresh, this random key will be randomized, regenerated. It'll be a different random key every single time. Server is going to respond with a 101 response, which is switching protocols, our first 100 level response. I believe our only one for this course. A 101 switching protocols. We're going to have three headers ourselves. Two of them are the same. Yeah, we're upgrading to WebSockets. And a sec WebSocket accept header with a very specific accept response. So this is the structure that we're going to do, and the next slide is going to have quite a bit of details on how to go from this random key to this accept response. This accept response is generated from that random key, and if we don't compute that exactly, the browser is going to check this. If it's not exactly what the browser expects, the connection won't be upgraded. We won't have a WebSocket connection. Yeah.
Is there any time when we would get a request to make an upgrade to a WebSocket that we wouldn't want to do it?
In theory, no. In practice, probably. So that would be if somebody's trying to modify your front end and probably trying to attack you, and you're not set up for that. The WebSocket connection should be coming from your JavaScript code. And if there were a case where you don't want to allow the WebSocket connection, you would probably change that JavaScript code to just not send the request. But if somebody's hacking your front end, that's something we always have to be aware of. We might be getting requests that we don't want to allow. One thing I can think of is if somebody wants to hit us with a DOS by opening a whole bunch of WebSocket connections that have to persist, and maybe we're threaded for each connection on our server side, they can shut us down real quick. If somebody opens, even the simple open 300 tabs and just leave those connections open, or write a script to do it much faster. That I could see, but that's in DOS protection territory. Okay. So the last piece of this, this is most of, we already talked about most of establishing the connection, but the rest is the guts of how to go from this key to the accept. So we take the key, this random value, and we're going to append to the end of it this string. Man, the highlighting in these slides. Give me just this highlighted. Is that too much to ask? Hey, I got the open quote, not the closed one. That bugs me, but we're living with it. This exact string. This is part of the protocol. If you go to the RFC has this exact string, this globally unique ID. This is an ID for the WebSocket protocol, that exact string. We're going to concatenate that to the end of the key. We're going to compute the SHA-1 hash of that concatenated value. And we're going to base 64 encode that hash. And that's how we generate the WebSocket accept. I'll go through some examples. I'll explain that more in depth. But this half a slide right here, that's the bulk of, at least the difficulty of Objective 1 on the homework, is making sure you're getting all this right, looking up libraries. And you can use libraries to compute SHA-1 hash and base 64 encoding. I'm not going to ask you to do those on your own. Any libraries, any language you're using should have both of those built into the language itself. If it doesn't, feel free to import an external library to do the hashing and the encoding for you. SHA-1 hash is an encryption algorithm. I'm going to assume that you're familiar with those. You're going to take a hash of that. If not, actually, we will talk about encryption and hashing. Did I say it's an encryption algorithm? I didn't say that, did I? It's a hashing algorithm, which is something we'll talk about in Homework 4 content. When we're handling user passwords, we're going to hash those passwords, something most of you probably heard me talk about in 199. Now it's your turn to actually hash those passwords and hash them and store them in a database. It'll be written code to do all that. And then base 64. So when we take the SHA-1 hash, we're going to get a bunch of bytes. Those bytes are, in all likelihood, not going to be in proper ASCII values, or UTF-8 values even. They're not going to be able to be encoded into text. Much like our images, we had to make sure those never turned into text. But now we have a problem that we have this SHA-1 hash, which is just a bunch of bytes that aren't going to be UTF-8, and we have to put them in a header, which is ASCII only. So this is a problem. Base 64 is the solution to this. Base 64 is going to take bytes and encode them as strings. So this is something technically you could use with your images, but it would be much more difficult than the way I explained it in lecture. You could base 64 your images, send the strings, and then have the browser decode the base 64 encode it. It'd be a mess, but technically you could do it. But base 64 is going to solve that problem, taking random bytes, whatever byte sequence we have, and encoding it as a valid ASCII string. So the base 64 part is just to be able to get these bytes into the header. Don't ask me why they don't just take the hex values for the SHA-1 hash. I don't have a good answer for that. I think that would have been a lot easier. Just use the characters 0 through 9, A through F. I don't know. That's not the way it works. We're going to base 64 encode because that's what the protocol says. So why do we do all this mess? One, the one that I talked about already. We want to make sure client and server are both speaking the protocol. There is zero, so hesitant to say zero. There is an infinitesimally small percentage probability that a server that doesn't speak WebSockets and isn't going through this procedure is going to generate the correct accept. For all intents and purposes, it will never happen. It's never going to happen. So if somebody generates and responds, if a server responds with the correct accept, that browser can all but 100% guarantee that that server does properly speak WebSocket, it speaks the protocol, and we successfully upgraded to WebSocket protocol. To do this just by random chance, I mean, it's way too, no, it's not going to happen. But technically possible, so say highly unlikely. And two, to avoid caching. The requests and responses are never going to be identically the same. They're never going to be identical, so things won't be hashed. If we have a really aggressive proxy or inverse proxy server, it's not going to hash these things because they're going to be different requests every single time because we have this random key. I should probably explain that a little more. Like a reverse proxy server is having a server in between the client and your app that's forwarding requests to your app. And there's a lot of different reasons we want that. Load balancing. I use Nginx on my servers because I have multiple apps hosted on a single server, and then Nginx routes everything to the proper app for whatever domain name was requested. But Nginx has some pretty aggressive caching. We want to make sure Nginx doesn't get in our way because it doesn't make sense to cache a request for to upgrade protocols. It doesn't make sense. So we want to make sure Nginx doesn't hash that thing, or Apache, or whatever we're using. Then once the connection is established, we're going to send WebSocket Frames back and forth. This is where things get fun. I get excited about this. I don't know how excited students get, how much excited y'all get. But when we're into WebSocket Frames, this is how we're going to send information back and forth, the format of those. And when we're working with frames, we're getting into bit parsing. So we start off in this class parsing strings. We move on to parsing bytes for homework 2. For homework 3, we're going down all the way down to bits. I get excited for this because in courses like 191 and 341, we learn about all this low-level bit stuff. We're told that machines are always ones and zeros and stuff, but we never really feel that when we're coding with high-level languages. But here's a case where we're going to use high-level languages, Python, JavaScript, Go, but we still have to be aware that even our ints and our bytes especially are encoded as ones and zeros. And we're going to have to parse at that bit level. So this is the format of a WebSocket frame. Like I said, I'll go into this in detail on Wednesday and then give examples on Friday. But just to foreshadow this a little bit, these are the bits. Each bit, we're going to have a fin bit, 3 reserve bits, a 4-bit opcode, a 1-bit mask flag, a 7-bit payload length, and then potentially a longer payload length. We'll talk at length about payload length. A 4-byte masking key, and then finally the payload of the message, the actual message that's being sent. So there's a lot of this where we have to pull out individual bits. If we want to get the mask bit, we have to pull that out. The big thing that you'll have to do in your homework is finding this byte right here and extracting just the last 7 bits to get the payload length. That'll be the most important thing that you have to extract. The first 2 bytes actually have simplifying assumptions. The first 2 bytes will always be the same for your homework. I wanted to get something where you have to read these, but there's only one thing that really makes sense to do, and that's the opcode. There's 2 different opcodes I could read, but I don't know. Reading payload length and parsing through that, you'll have enough fun with that without parsing everything else. All right, so more about that on Wednesday. These, well, except this. I guess this is cutting into Wednesday's content a little bit. But masking, the client's going to send a masking key, which is 4 bytes of 4 randomly generated bytes. And then the payload of the data, each 4 bytes of the payload will be XORed with that mask. So the payload isn't just going to be the straight up data that we receive. It'll be the data masked with those masking bytes and by XORing each 4 bytes of the payload with the masking bytes. So why do this? That just seems silly because now we have to read the mask, unmask everything, and then read the data. It's just a lot of extra steps. Why? Again, to prevent caching. If somebody sends the same message to our chat twice, we don't want Nginx or Apache or some other middleware or middle server, would we call it at that point, getting in the way, caching that, and saying, oh, you already sent this to this server over this TCP connection, and last time the server responded with this, so I'm going to respond with this without talking to the server. Well, now that message never made it to our database. It never made it to other users. We don't want that. We want to avoid caching. So masking is going to avoid all that caching. It's going to make sure that our server actually receives everything that was sent by the users, with high probability at least. We have 4 bytes of random stuff. We got 2 to the 32, 1 over 2 to the 32 probability of a collision if they send the same message. We got pretty good odds on our favor. On the browser side, this is what our WebSocket code is going to look like. We're going to create the connection by using new WebSocket, use the WebSocket protocol, get the host. I recommend getting the host this way. Get the host dynamically. Don't hard code localhost, please. And once you go into your Docker container, it's not going to be the same. Don't hard code 0000. Always grab the host dynamically. This is a mistake I see a lot, not necessarily in this class because you'd probably get away with it anyway. But out there in the real world, if you hard code anything here for the host, guess what happens when you go to deploy on production when you have a domain name? Whatever you put there for host is not going to be your domain name. And if it is, you have separate code for production and separate code for your development environment where you're testing things. If you just get the host dynamically, it's the same code for localhost, for development, and for production when you have a domain name. Your domain name can change. Your code shouldn't change when your domain name changes. Don't hard code this. Just grab the host dynamically. And then the path where you're listening for WebSocket connections. So if you have the big else if, by the way, the 3rd week of this homework, there's some time in the schedule. I want to give an example of getting rid of that big else if block. I want to finally show an example. I keep teasing that. I want to get a good example ready, prep for lecture, and show it to you. But in your big else if block, else if request type equals get, path equals socket, do all your WebSocket stuff. Look for that key, generate the accept, and send your response, like we talked about in the previous slides. Whenever we want to receive a message, where's my on message? There it is. We're going to take this socket that we created and set its on message field to a function that's going to take the message and then do whatever we need to do with the message. The browser's going to do all of the parsing of the frames, all the WebSocket frames. The browser's going to do all that for us and just give us the content. Just give us the payload of that WebSocket message. So whatever the server sent, and here I'm just logging it, but this is where you would add it to the chat or do whatever we want to do with that. And then to send a message, we're going to use socket.send and give it any string. And then again, the browser's going to create the masking bits and set the payload length and create that whole WebSocket frame and send it to the server over that TCP connection. So client side, this is it. The browser does all the work for us. And if we could use web frameworks, server side would be just as simple too. But since we had to start with TCP sockets, we get to get into the details of how WebSockets actually work. And that's the handshake and parsing WebSocket frames and creating WebSocket frames. All right, so I want to do a little bit of a demo. I did it 2 demos ago, didn't go so well, so I'm always nervous in this class now. But we're going to check out some WebSockets. Oh, I need to mute. We're going to go into someone's chat. Oh, I kind of want to unmute that. It's pretty neat. Looks like something's going on. I'll mute the ad. But what I want to do, actually I have to refresh anyway, so we might get a second ad. Yeah, great. So want to go to network. Refresh. And we can see all the Ajax requests. Fired off there. I'm going to sort by status. I'm going to look for some that responded with a 101. This is going to be my WebSocket request. The one for Twitch chat. And we can see the request headers. We're going to see the 3 headers that we expect. Upgrade WebSocket, connection upgrade, and the WebSocket key. This WebSocket key is the one we're really interested in. This WebSocket key is the one we're really interested in. And then the response is going to have this WebSocket accept. So when you're coding this, it's going to be hard to tell if everything works. You run your server, go to the browser, and make sure that the WebSocket connection, was made properly. That can be a little tough. But what you can do is go to any website that uses WebSockets like this, go to the requests, check out the 2 headers that we're interested in, key and accept, and right there you have a test case. There's a test case, and you want to write a function that takes in the key, returns the accept, and do that until your test case passes. It's going to really speed up your development process. You have an infinite number of, I shouldn't say infinite, but you have as many test cases as you want. You can go refresh again. It's going to be different values. Go to each request. You're going to keep seeing those values. So let me go to text edit here, new document. And we're going to try to generate these keys. This is the part where I hold my breath a little bit. Oh, why is that? Okay, so that's what we started with. This is what we want to end up with. And I'm not going to do this with code. Obviously, your goal is to do this with code. Oh my goodness, thank you. It would have been bad. You're killing me. I mean, that one was my fault, I guess, but aren't these labeled at the same time? I think this one's background. Okay. And make it bigger. Okay. So that's our starting point, and that's what we want to end up with at the end. So I'm going to just do these with online calculators and try to get from that value to the other value, just to verify that this is what's happening. So I want to do a SHA-1 calculator, like this one. We're going to paste this value. We're going to go to the slides and grab that global unique ID. If it can select this time. Good enough. Get rid of the quote. Make sure we don't have any trailing white space. I'm going to compute the hash. I'm going to go paste this intermediate value. And now I want to base 64 encoder. I'm going to do this intentionally wrong the first time. So this one should not work. I'm going to go to this, paste my text, UTF-8, that's fine. Well, I guess I can do ASCII. And encode. I should get something that's wrong on this one. One thing to be careful with this, when you're doing the base 64 encoding, don't use a string encoder. So this is taking this as a string and not as bytes. What we want to make sure we're doing is interpreting these as bytes. This is hex. So what I want to do is hex to string base 64. And I want to get a hex to base 64 encoder. And this one should give us what we want. So there's your proof of concept that is exactly what we're doing. We're appending that GUI to the end of the key, SHA-1 hash, base 64 encode from hex to a string. I'm glad that one worked well. There's not too much that could have went wrong there, but that's exactly the process to generate that. You can get as many test cases as you want. Just go to a site with WebSockets, get your test cases, and use that to verify that your code is doing exactly what we just did there. With that, I don't have anything else, so see you all Wednesday.